All right, so we've reached the point in the course where it's time to basically set up our second major problem of introductory level physics. We said that there's sort of two big problems, one of which, of course, is Newton's second law, which is where we learn how to keep track of forces and use them to figure out how an object's motion will change. So our other big problem is going to be learning how to keep track of energy. And so the sort of the baseline way that we're going to do this, and what we'll see is the work-energy theorem we'll use to build into our energy balance equation that we'll use to talk about conservation of energy. So all those things are very much connected. And so what we're going to do is we're going to start by talking about the work-energy theorem. So this is kind of the fundamental equation in some sense that we'll use to set up our second big law or big problem of introductory physics, which is conservation of energy. So for starters, let's start by defining what net work is. And again, the key here is the net out front is telling us that we're going to add stuff up. So the net work happens to be the work done on an object by all the forces acting on the object. In the same way that the net force was the sum of all the forces, one way to think about the net work, so there are three different ways that we can think about the net work done on an object, but the easiest is, well, it's just the sum of the work done. So the net force, sum of all the forces, the net work, sum of all the works. So one way to think about the net work is it's just the sum of the work done by all the individual forces acting on an object. So if you've got 1, 2, 3, maybe even more forces acting on your object, the net work is just going to be the work done on your object by force 1 plus the work done on your object by force 2 plus the work done on your object by force 3 plus however many other work terms you need for all the other forces that are acting. So this is one way to think about the net work. Another way to think about the net work is that it's the work done by the net force on an object. And if we have a special situation where the net force is constant, then we can calculate the net work the same way we would calculate the work done by any constant force. It's just that here, this happens to be the net force that we're putting in there. So again, the net work is just going to be the magnitude of the net force times the magnitude of the displacement times cosine phi, where again, this angle phi is defined to be the angle between the net force and the displacement. Now, the third way that we can think about the net work done on an object is that the net work is equal to the change in the kinetic energy of an object. And so what this does is it leads us to the work-energy theorem. So the work-energy theorem tells us that the net work is equal to the change in the kinetic energy of your object. So where we want to start then is talking about, so what does that mean, right? What's the work-energy theorem trying to tell us? Well, one way to think about it is that if the net force acting on the object has a component that points in the same direction as the displacement, then you know that the net force is going to do positive work on the object. So that basically means that given how we've defined calculating the work done by a force, if I know that the force and displacement point in the same direction or have components that point in the same direction, then that work term will be positive. Well, if this side of the equation is positive, then the delta K side of the equation also has to be positive, which means that your kinetic energy had to increase. On the other hand, if the net force points in the opposite direction of the displacement, or has a component that points in the opposite direction as the displacement, in that case, then the net work will be negative, which means that delta K will be negative, which means you will decrease the object's kinetic energy. Third option, of course, is obviously that if the net force does no work on the object. So if the net force does no work on an object, then there's no change in the object's kinetic energy. So what this means is that the net work is basically trying to tell us about how energy is transferred to an object to change its kinetic energy. So net work being positive, you're going to increase the kinetic energy. Net work being negative, that means that You're taking energy away in the form of kinetic energy. So you're taking kinetic energy away from the object. If the network is 0, then you're not changing the kinetic energy. All right, so fundamentally that's sort of what the WorkEnergy Theorem is trying to communicate. Now, what we can do then is we can come back and think about, well, how does the block's speed change as it's sliding down some incline? So let's set up this scenario here. So first, let's say I've got a block and it's already moving, it's sliding down the incline, so it's got some speed v that it's traveling with some velocity v here as it travels down the incline. And I am going to start pushing, so at some instant, I'm going to start applying a force that points back up the incline. Okay? And so what I want to think about then is how does the block's speed change based on how I'm pushing. So again, it was at the instant I start pushing, it's traveling down the incline with some velocity v. I want to think about how that speed is going to change. Now, we can think about this problem, and we will to start with, from a Newton's second law perspective. So from a Newton's second law perspective, we would say, well, we need to think about the free body diagram of the object. Again, our object's got mass, so there's going to be a weight force. It's in contact with the surface. There's going to be a normal. Let's assume that the surface is frictionless. That way I don't need to worry about friction. And then I'm going to apply this applied force pushing back up the incline. So here's the free body diagram that I've got. Again, thinking in terms of Newton's second law, I know that the acceleration is going to lie along the incline. Right? The block's not going to accelerate up off the incline or down into the incline, so my acceleration has to lie along the incline. So it's probably most useful to think about my forces in terms of breaking them up into along the incline, which I'll call the x, or perpendicular to the incline, which I'll call the y. The normal lies along the y, the applied force lies along the x. It's just the weight then that I need to break up into x and y components. And again, since I know that my block is not accelerating in the y direction, what I call the y direction, right? There's no acceleration perpendicular to the incline. That tells me that this component of the weight, the y component of the weight here, has got to be the same as the magnitude of the normal force. What's going on with the speed then cares about how the magnitude of this applied force compares to the component of the weight that points along the incline. So if the magnitude of this applied force is larger than the component of the weight along the incline, then when I add these two when I add all my forces together, this component and the normal will cancel. The applied will be larger than the component of the weight along the incline, and so my net force will point back up the incline. Newton's second law says that means my acceleration will point back up the incline. And then we know that if the velocity and acceleration point in opposite directions, that means that my block is going to slow down. So here's a situation where I'm pushing hard enough that the acceleration points in the opposite direction as the velocity, and my block slows down as I continue to push. So what if I make that applied force much smaller? And in this case, what if I happen to make it smaller, the magnitude of the applied force is smaller than this component of the weight pulling the block down the incline? So again, my normal force is still going to be, its magnitude is still going to be canceled out by the y component of my weight. But now when I add together this component of the weight and this applied force, now I get a net force that points down the incline, which means my acceleration has to point down the incline. The acceleration and velocity point in opposite directions, in this case the acceleration and the velocity point in the same direction, which means my block speeds up. Now, it's not going to speed up as much as if I wasn't applying the applied force. Right? So if I don't push on it at all, the block's going to continue to have the same acceleration it had before. It's going to continue to speed up. By applying this applied force back up the incline, because it's small enough, it's still going to speed up, just not as much as it would have if I didn't start pushing it. Well, the last option is obviously if I happen to apply just the right applied force such that its magnitude is exactly the same as this component of the weight pulling the block down the incline. So again, now I know when I sum up these forces, net force is 0, which means the acceleration has a magnitude of 0, which means that the block travels at a constant speed. So this is all stuff that we've talked about, that we're comfortable with in terms of thinking about Newton's second law. So when we start to think about the work-energy theorem, the first thing we know, or what we need to recognize, is we've got to get the same answer, right? The work-energy theorem can't tell us something different about how the block's going to behave. So let's see what the work-energy theorem does tell us. So one way to think about the work-energy theorem is, again, to think about the net work as the work done by the net force. And what we said is if I have a large applied force pushing back up the incline, then when I add together all these forces, I get a net force that points up the incline. Well, the displacement in this case is down the incline, right? The block's going to keep sliding down even as I'm pushing on it. So now I look at the fact that the net force and displacement point in opposite directions, which means that the net force has to do negative work on the block. That negative work is going to take kinetic energy away, so I have a decrease in the kinetic energy of the block, which means that the block slows down. So notice I get exactly the same answer that we did before. The block's going to slow down if the applied force is large enough, so that my net force points up the incline. If I make my applied force small, so its magnitude is now less than the component of the weight pulling the block down the incline. Again, now this means that my applied force, or that the net force points down the incline. Now it points in the same direction as the displacement. The net force and displacement pointing in the same direction means the net force does positive work, so the net work is positive. If the net work is positive, that means I'm increasing the kinetic energy. Increasing the kinetic energy, the block has to speed up. So again, I get the same answer we did before. Third option, of course, is if the applied force has exactly the right magnitude to cancel out this component of the weight, which means now the net force is 0. If the net force is 0, that means it does no work on the block. Right? If the net force does no work on the block, that means the kinetic energy doesn't change, the block slides down at a constant speed. So notice I get the same answer with the work energy. Now, in the way that we sort of talked about this, notice that basically what we've done is we've still thought about it in terms of going ahead and doing this vector addition problem to think about the net force first. As a general rule, when we're working these problems using the work energy theorem, what we're really going to do is say, well, let's think about the work done by each individual force, and then see if that can tell us something about the net work. So the way that we'll tend to work this problem, and let's come back to our initial situation where we've got a large applied force pointing up the incline. Well, the first thing we're going to recognize is the displacement points down the incline, which means when I think about the work done by each of these three forces, well, the normal is perpendicular to the displacement, so the normal is going to do no work. The weight, right, the gravitational force, it has a component that points in the same direction as the displacement. So gravitational force has a component that points down the incline, displacement points down the incline. So the weight will do positive work. The applied force, it points in the opposite direction as the displacement, so the applied force will do negative work. So the first thing I can do is say, well, I know the normal is going to do no work, the weight will do positive work, the applied force will do negative work. So thinking about the net work means I need to think about, well, which of these is larger? The work done by the weight, positive work done by the weight, and the negative work done by the applied force. Since both of those forces are going to act over the same displacement, then basically what I care about is, well, what's the component pointing either in the same direction or in the opposite direction, and I know that the component of the applied force is larger than the component of the weight. The points in the same direction as the displacement, which tells me that the work done by the applied force is larger and negative. So the applied force does more negative work on the block than the weight does positive work. Which means when I add these three things together, I'm going to take 0 plus a positive number plus a negative number that's even larger than my positive number was, which means that I have a negative net work. Negative net work means I have a decrease in the kinetic energy and the block slows down. So again, I get the same answer. Now I'm just thinking about the work done by individual forces and then adding those up to get the net work. If I have a small applied force, well again notice the normal is still perpendicular to displacement, it still does no work. The weight still has a component that points in the same direction as the displacement. It still does, the weight does positive work. The applied force still points opposite the displacement, it still does negative work. But now, because this is a much smaller applied force, and in fact it's smaller in magnitude than the component of the weight that points in the same direction as the displacement, this tells me that now the weight force does more positive work on the block than the applied force does negative work. So when I add these three things up now, 0 plus a positive number plus a negative number that's less than my positive number, the net work is going to be positive, which means I have an increase in the kinetic energy, which again tells me that my block speeds up. Last option, again, none of this changes, right? My signs don't change because I've still got a normal that's perpendicular to displacement, weight that has a component that points in the same direction, applied force points in the opposite direction as displacement. But now the magnitude of the work done, or the work done by the gravitational force, its positive number is going to be exactly the same as the work done by the applied force. It's just that one will be positive and the other will be negative. So when I add them up, I get 0. Plus the work done by the normal, that's also 0. So I see that here the net work is equal to 0 because the gravitational force does the same amount of positive work on the block as the applied force does negative work. If the net work is 0, then the kinetic energy doesn't change, which again tells me that my speed is constant. So for starters, we get the same information. Okay? And so just to summarize what that information is, if the net work is positive, it tells me that I'm adding to the kinetic energy of my block, or system, whatever it is I'm keeping track of, which means the final kinetic energy is larger than the initial kinetic energy, which tells me that my object is speeding up. And that happens because the net force, one reason to think about why that happens is because the net force and the displacement point in the same direction. Another way to think about it is that all of the forces that are doing positive work do more work on my block than the forces doing negative. If the net work is negative, then I'm subtracting kinetic energy, which means that the final kinetic energy is less than what the initial kinetic energy was, which means that my block slows down. And again, one way to think about this is that the net force is in the opposite direction as the displacement. Again, our other option in terms of thinking about this is that all the forces acting on the block to do negative work, that sums up to be more than all the positive work done by forces that point in the direction of the displacement. Third option, if the net work is 0, that means there's no work done on the block or on my system, which means I'm not changing the kinetic energy. The final and initial kinetic energy are the same, which means it's traveling at the same speed at the beginning and the end. Now again, I've got some ways that this can happen. One is that the net force can be 0. Another is that the displacement can be 0. The third is that the net force can be perpendicular to the displacement. Another one can be that there's actually a region over which my block moves where the amount of positive work it does over some region of the displacement is exactly the same but with the opposite sign as the negative work done over some other portion of the displacement. So again, there are a couple of ways, right? I can have a situation where the positive work is done, negative work is done, but when you add it up over the entire displacement, you still end up with no work. So these are sort of my three options with what's going on with the work energy theorem. All right. So if I get the same answer using the work energy theorem as I do using Newton's second law, and we've already spent a lot of time working on and practicing using Newton's second law, why do I need another way to work these problems? Well, one is there's simply situations where we can't use Newton's second law. So again, we know using Newton's second law and then figuring out what's going on with the motion of the object means that we need to use our kinematic equations. And the kinematic equations we have demand a constant acceleration. So we don't actually know, and we could go through, but again, it requires calculus. So we're not actually even worried about situations or using Newton's second law in situations where we have non-constant acceleration. Instead, any situation where we know the acceleration is not going to be constant, we're going to use the work energy theorem. It just makes things much, much easier. Second is, we may have a situation where we only have information about what's going on at some point initially and what's going on at some point finally, and all the details between that initial and final state we don't know. Now the nice thing is that the work energy theorem doesn't actually care about what all those details are. They all sort of wash out. And as long as you know what's going on initially and what's going on at the end, we can still make the work energy theorem work for us. The second crucially important thing to sort of get across is that why we want a second way to work these problems is because as a general rule, the work energy theorem is so much easier to use. So Newton's second law was a vector equation, which means we had to go through drawing the free body diagram, picking a coordinate system, breaking up our vectors into components. And then we had an equation that we had to set up for every dimension that we had in the problem. So we might have 2 or maybe even 3 equations, which means that we'd have 2 or 3 unknowns, and we'd have to come back and deal with all those, and we'd have to pick the right coordinate system to make the math easy, and all that was involved. The work energy theorem is just a scalar equation. It's just numbers. So as a general rule, it's simply much, much easier to use. So we're going to use this, the work energy theorem, to work problems where sure enough we can go through and use Newton's second law. But we don't want to because Newton's second law is just going to take so much more work. Right? So when will we use Newton's second law problems? Sort of when do you have to? Well, usually it's easiest if you want to solve for the acceleration to work a Newton's second law problem. With your motion piece, if you want to solve for the time, work energy theorem doesn't give you any information about time. So if you want how long does it take to block to slide down the inclined plane, you still have to go through and do your Newton's second law problem. So you have to solve for the acceleration and then go use the acceleration, plug it into your kinematics equations to solve for time. If you wanted direction, again, because this is a scalar equation, we lose information about direction. So again, as a general rule, if what you wanted was the direction at which your object was traveling at some point, you would still want to use Newton's second law. But the most common question we get in terms of an object's motion is about its speed. And when you want to solve for the speed of an object, because speed is a scalar, right? It's just the magnitude of the velocity vector. I don't care about direction, I just want magnitude. If you just want the speed, then the work energy theorem is the best friend you have. Almost always, it will give you the speed quickly and easily, as long as you sort of understand how you need to work with work energy theorem problems. So this is what we're going to do sort of going forward, is we're going to say, if I need acceleration or time or direction or velocity, I still got to go work a Newton's second law problem. But if all I'm interested in is the speed, I'm going to use energy. Because energy is going to get me the right answer, and it's going to do it in a much simpler way.